presenter, so clarification questions, and you can test him a little bit, but that's it.
119,833. It's the number of people currently on the organ transplant waiting list in the United States. 22. That's the number of people who die every day waiting on the organ transplant list. My paper takes the first steps into looking for a solution to the amount of deaths that occur while waiting on the organ transplant waiting list. So my paper is titled A 3D Bioprinting System to Produce Human-Scale Tissue Constructs with Structural Integrity. In simpler terms, 3D printing functional human tissue structures. First, I'm going to talk to you about the printer that the researchers use. So this printer is called the iTop, or the Integrated Tissue Organ Printer, and it has multiple dispensers, as you can see here. So this allows the printer to create one uniform tissue structure. So you can see the dispenser with the gray is used to print the PCL, or the polymer, which keeps the tissue structure stable. And then the rest are used to print the cells or the different structures, such as the hydrogel, which surrounds the tissue and provides structure until it's implanted into the environment. So here you can see a picture of what the tissue would look like, and up close what cells would look like in the tissue. So you can see the two cells right here, and then the gray on the outside is the PCL, which provides the more support, and then the microchannel in the middle, which I'll talk to you next. So the microchannels are created by the iTop, and it allows oxygen and nutrients to flow throughout the tissue and into the cells to allow them to maintain viability and continue to grow. So you can see here that these are actual pictures of the 3D printed cells, and the microchannels are in between the cells within the tissue. So first, the researchers 2D and 3D printed cell patterns in order to test the accuracy and see the cell viability of the printed cells. So you can see here they just printed these random characters, and it looks pretty accurate. And then the researchers looked at the viability of the cells for up to 6 days after. You can see that the cells remained 100% viable 6 days after they were printed, showing that the printer not only is accurate, but it's able to print viable cells. So next, the researchers found that they can print 2 different cell or tissue designs using the iTop printer. The first is the type 1 design, and it has layers of cell and polymer, so it's a more structurally stable design. Yeah.
Sorry, on the last slide, how did they test cell viability?
They didn't specify, but they saw like what % of cells were still alive. So the type 1 has layers of cells and polymers, which allows the structure to be more stable, and you can think of it kind of like a wafer cookie with the different layers. And this would be used for ear-shaped cartilage or mandible bone constructions. And the other is the type 2 cell design, and it's a more protective design because you can see here that there's a layer, kind of a cage of PCL on the outside, and this would be used for constructs like skeletal muscles. So first, the researchers did a mandible or a jawbone reconstruction, and you can see here, first they modeled a defect of a human jawbone on the computer, and you can see that the printing of the jawbone defect is almost exactly the same as the model on the computer, which is great because it shows that the printer is able to be very accurate, and then the printed bone will be able to fit right into the area. So after 28 days of implantation, the researchers looked at the bone, they stained it, and saw that there was calcium in the bone, which means that it was receiving nutrients and oxygen and continuing to grow, which kind of shows that this was successful as the bone was able to integrate into its environment. Yeah. So can anyone remind me what the difference between type 1 and type 2 cells are?
So type 2 cells are more often used for muscle because they have more protection with that cage around them.
And type 1?
And type 1 is more protein, so like bone, softer bone and cartilage.
Okay, so next the researchers did a calvarial bone reconstruction, or a reconstruction of an area of the skull cap, and they used rat bone cells, and constructed circular areas of the skull cap and implanted them directly into the skull cap of the rats. You can see after 5 months, it looks like it's kind of molded into the rest of the bone, which shows that it's able to integrate into its environment and maintain viability and continue to grow even 5 months after implantation. So here, this is just another picture of the area. So here, this is before implantation of the bone, and after you can see that there's new bone formed. And before and after, you can see the red is showing blood flow in the bone, which shows again that it's able to integrate into the environment and continue to grow. Next, the researchers printed ear-shaped cartilage, and to do this, they used the type 1 structure, and they used rat cartilage cells to print the human-shaped ear. Here you can see the steps they took. So first, modeling it on the computer and using different imaging softwares, and then here's an actual picture of the printer printing the ear, and then the ear. So again, the researchers used rabbit cartilage cells to print the human-shaped ear, and then took this human ear made of rabbit cells and implanted it on the back of a rat. So you can just imagine a rat running around the lab with the human ear on its back. So they allowed the ear to grow for 2 months, and you can see here, this is showing the blood flow. So from 1 month to 2 months, there's an increase in the blood flow within the ear. Again, showing that the ear is able to grow into its environment and maintain viability. So here you can see just another picture of the ear. So next, the researchers did a stress strain curve test on the ears to test the structural integrity of the ear. So you can see before implantation, there was the curve shows the amount of resistance. So before implantation, there's not really that much resistance. But after implantation, you can see how the amount of resistance has grown a lot, showing that the ear is receiving nutrients, and the nutrients are helping it to grow and maintain its structure and gain strength. Lastly, the researchers printed a skeletal muscle construct, and you can see here where they implanted the skeletal muscle in the rat and an actual picture of the skeletal muscle. And 2 weeks after implantation, the researchers stained the muscle cells and found that they were all still viable. They were all still alive and continuing to grow. Yeah.
Did they mention how successful they were in printing them? Like, was it every time they tried to print something that worked, or?
You mean like if they were failed structures?
Yeah, did they mention a failure rate?
They didn't talk about that. No.
So like when they're printing ear, like do they have to print like blood vessels and stuff like that inside the ear too? I'm sorry.
Well, they're printing like each cell is getting. They have in the dispensers that I showed in the beginning. They have like cells in them. So the 4 dispensers have like they kind of this. They print each of the cells like in the structure, but they didn't really talk about if they went into the blood vessels. So overall, the researchers, the printing of their tissue structures were they were viable, and they were pretty successful as they were able to integrate into all of their environments, and they were able to continue to grow. But they didn't look into possible rejection factors, because in normal organ transplant, there's always the possibility of rejection of the transplanted organ. So you never know if maybe these tissues will be rejected by their recipients. And they didn't test the function of the printed tissues, whether the ear would work after being implanted back on the human head, or if how well the muscle worked after being implanted into the body. So I have 2 questions for you guys. First, how do you think that these findings will affect the future of prosthetic and reconstructive medicine? Yeah.
I think it's kind of dependent on what you said in the last slide, whether they'll still have the functionality of like the organs or the muscles that they're replacing, or if they don't have the same functionality, then that would be a huge like leap forward, I guess. You wouldn't rely on the built organs or the tissue.
If you print it, if you have enough precision in the printer to print it exactly to that specific human, which can probably significantly improve rejection. There's a lot of
Great. Anyone else? Okay, and lastly, after these 3D printed body parts are implanted into the human or a mouse or anything, do you think that these parts are now considered part of the human body, or will they always be considered foreign?
if the body recognizes it as a part of the body and is like integrating it by like the blood flowing through it and like obviously the nutrients flowing through, then I guess it is part of the body.
The body replaces cells all the time. It's like not much different. Just putting it here, but it's a body part.
Any?
Not to be a devil's advocate, I have a hard time like thinking that it was only coming out of the machine out of the printer is part of my human body, so like I think that would be a part of the state of
Well, I mean, since there are different dispensers, it depends what like cells you load with them. So if it comes from the person who's going to be receiving that new body part, it's still their cells being like utilized to build themselves a more efficient, I guess, organ. So I think it's similar to the human body if it's their cells.
What cells were they using? Like, where did they get the cells from? Like the specific one?
So for the mandible bone, they used human stem cells, and then for the others, for the ear they used the rat cells, and then the other two they used mouse cells.
Like where did they get that cells?
Oh, they didn't specify that.
Harvest them and grow them in the lab.
But like from those actual.
Yeah. Early development.
Would you guys completely hold at least most of the cells that you do with the body? Because the cells will die.
Probably.
Well, I think it's kind of like when you get a transplant. Like, you get like a heart transplant. You have to like ask yourself, is it my heart or it's actually someone else's heart? Someone else's like DNA that's gonna be in me forever. So is it part of my body or is it someone else's body inside me?
Are the nerve cells there? Like if it's an ear transplant and then you can pinch your ear and you can feel that, would you be able to feel it if it were a 3D part of your
I'm not sure. They didn't really talk about because they didn't talk about the function or how it would work, how well it would work. Not much.
Wouldn't there always be like better rejection because of the culture? That's always there, right? Since it's already not
Yeah, I think so. But the researchers they didn't look into it at all. So that's like some of the next steps.
It was also probably developed to be like not rejected by the body. Like if you were here last week, is Mira not here? Oh, not last week, 2 weeks ago with Kelly's presentation, she talked about the biocompatibility and whether or not like rejection would happen with something that's created in a lab setting.
Anyone else?
Did they look into the cost of it at all, relative to other transplant procedures or other prosthetics?
No, they didn't discuss that, but I would imagine that it's much more expensive because they're printing it for each individual person, so it has to be very specific.
So in the short term, would they imagine, I mean, well, not necessarily short term, maybe in the short term, would they imagine this supplementing the organ donor list or with the goal of eventually replacing it, or?
I think so. It's kind of another option, but it's not like an option for everyone because I would imagine it's so expensive.
I think the benefit would be that the more wealthy people who could be able to afford this type of like whatever they need, if they can get those people off of the waiting list, then they're giving more opportunity to those people who don't have the money and like could possibly move up in the transplant. And another point is that for the ear specifically, like the shape of the ear just like funnels the sound within the eardrum. So specifically for the ear example, like it would aid these people's hearing, but it wouldn't necessarily like they don't need like functional like shape of the ear, but it can benefit people who like lose their ear because of their burns or something like the shape of the ear is like so I think like just to go off that way.
Anyone else? Okay. I'd just like to thank all these people. The presentation would have been possible without them. Thank you.
So do
and in the problem they use human cells. So those human stem cells, are they like human stem cells repositories where you just like go and grab some to make your reproduce parts, or do you know how that works? Like how do you gain those materials?
Not really sure. I know they use human amniotic fluid-derived stem cells, which are like the stem cells that differentiate into bone. I don't know where they got them from. Yeah.
Back in like one of your first slides when you were talking about the actual mechanism of 3D printer, you were talking about the microchannel.
Mhm.
You said it was made of polymer. Did they specify like what?
No, the microchannel is just like a hollow area in between the polymers, like on surrounding the two layers of cells to keep the stability. So the microchannel is just kind of an empty area which allows the nutrients and oxygen to flow.
I know that you said that they didn't really look into how we function afterwards, but do you see potential in this field to create something that's almost like genetic engineering, where people might say that if you can create a muscle that actually functions better than a normal muscle, that it could be giving some people an advantage? Do you see that happening?
I think potentially, yeah, it could in the future happen, but as of now, it's like a very small scale that they're doing this on, so I don't think, not in the near future, but sometime.
And then just to like throw off your idea, Lindsay, with like everybody considers their organs to be like essential. You take care of your body because you only get these organs once, you know. So if you can just grow them in a lab, just to get another one, like how would that affect the way people live, the way people behave and interact? If you can just get another organ.